we are discussing the combinatorics, that means mainly the counting problems with arrangements, and in particular the ordered arrangements, that means the permutation, and the unordered arrangement, that means the combinations. Now, the last lecture we have read the permutations, mainly the R permutations of a set with having n elements, or R combinations of a set having n elements. Now, today first we will see that permutations of multiset, that means R permutations of a set where the elements are not distinct. Normally, the set we define where the elements are distinct, and we define that type of set as a multiset. So, we will read the permutations of multisets. So, a multiset is a set where elements are not distinct. So, if elements are not distinct, that in other way I can tell that elements are with repetition, that means set with the repetition of elements, that we can tell as a multiset. So, I take one example, that say M is a multiset, and M I can write, say I have A, there are 3 A's, 2 B's, then C 1, I have say 4 D. So, it has 10 element set. Now, I can write this thing, since A, B, C, D, they are not, there are 4 different types, but they are not distinct, and the same thing I can write as if A with 3 repetitions. So, normally we define or we denote this thing as a 3 dot A, that means A of with repetition 3, 2 dot B, B with repetition 2 repetition, 1 C and 4 D. So, there are 10 element, this is a 10 element multiset. So, M is a 10 element multiset. Now, it may happen that there is no restriction of some particular elements, that means that we can tell that infinite elements, these are finite number of elements exist. Now, if infinite, if some element appears in the set, or I should write the multiset, infinite time with infinite repetition, then I can write the set M, say this is A with 3 repetition, B with infinite repetition, that I can write infinity dot B, again C can be infinite repetition, and then this is a, so this is and infinite number of elements multiset, there is no restriction. Now, with this introduction we try to define that the permutation of a multiset. So, as we have defined already that permutation, we have defined that this is an ordered arrangement. So, we will be counting the some objects when the arrangements in order. So, I can write that if S is a multiset and R combination, sorry, this is we are discussing permutation. So, this will be R permutation. R permutation of S is an ordered arrangement of R of the set S and S having n elements. So, this is same, only this is again ordered arrangement, only we have taken this is as a multiset. So, if I take an example, say M is a multiset and I have taken say A with repetition 2, then B with repetition 1 and C with repetition say 3. Then the if I want the R equal to 4 say, that means 4 permutation, that means that is 4 permutation of the set M some of the 4 permutations that be I can write A B C or A B C C. These are some of the 4 permutation. It can be that since it is ordered, I can take A C B C. I can take this type of ordered permutation. Or it may be B C C C, that is again another ordered permutation. Now, I have here the number of elements are in M, number of elements of 3 type ABC, elements are of 3 type and total number equal to 2 plus 1 plus 3 equal to 6. So, there will be no 7 permutation of M. So, at most we can take the up to 6 permutation we can take. So, at most we can consider 6 permutation, and normally if it is, and then it is called permutation only, because if it is n permutation of a set having n elements, then we call this is nothing but the permutation of all elements. So, this is called the permutation. Now, we see some property or so I give a theorem how to compute the R permutation of a multiset having n elements when it is finite, or we will see later if it is infinite. So, let S be a multiset with objects of k different type. Like last example we have seen ABC 3 different types. So, here k different types, where each type has an infinite repetition. Then the R permutation of S is k to the power r. So, the first theorem we consider that the multiset having infinite number of or having elements with infinite repetition number, and thereof k different types. That means, I can write that like M is a multiset. If I write that infinite of A1, then infinite number of A2, infinite number of A3, and in this way it is infinite number of AK. That means, here A1, here A1, A2, AK are k different type of objects. Or k different Now, how to prove this thing? How to prove this theorem? So, in constructing the R permutation, we have to construct the R permutation of this type of multiset we can choose of multiset M since every element appears or may appear infinite time. So, we can choose the first element or the first object first type of objects any one of the k types, right, as any one of the k types. So, since I have R permutation, so I take that first object can be chosen by k different ways, because any one of the k type. Second object, again that can be chosen by k different ways, and similarly if it is rth, because it is r permutation, so rth object can be chosen by k different. Since there is no restriction and any type of objects appears infinite with infinite repetition. So, with the multiplication rule, using multiplication rule, I can tell that R permutation of set M having objects with infinite repetition is equal to k into k into k r times. So, this is equal to k to the power r. So, the result is proved. Now, we see that application of this theorem. I take one example, one problem, how we can apply this one. So, I give one problem that what is the multiset with ternary numerals with at most 4 digits. What does it mean? So, with ternary numerals means my numerals can be only 1, 2 or 3, but obviously that set has the 3 type of elements. So, if I consider a set S, 3 type of elements, but all are of infinite with infinite repetition, because there is no restriction. Now, I have to form a 4 digit number, and I have the 4 digit number, like examples of 4 digit number only with 3 literals. So, that means it can be 1 1 2 3, it can be 1 2 3 2, it can be 1 2 3 3, and all this type of 4 digit numbers. Now, mainly we have to find out that what is the multiset, that means how many this type of numbers are possible. So, directly we can apply this result of this theorem, because here it is k to the power r. So, k is of 3 because I have 1 to 3 only 3 different types. So, k equal to 3 and r equal to 4 because mainly I have to take the 4 permutation since I have only 4 digits. So, 4 permutations of S and this is equal to 3 to the power 4 is 81. So, I have only these many numbers possible. Now, I give that finite if the theorem 1 tells that if the multiset have objects with infinite repetition. Now, we take if it is of finite number of repetition. So, I write theorem 2, write the statements of the theorem that similarly that S be a multiset with object of k different types with finite number of repetition. And I am writing the repetition numbers are n1, n2, n3, k different types. So, nk respectively. So, I can write or we consider that let size of S is n1 plus n2 plus n3 plus nk. So, number of permutation of S you can write is n factorial divided by n1 factorial into n2 factorial up to nk factorial. So, first thing is here theorem 2 tells about finite number of repetitions. So, let the k different types of elements are A1 to Ak. Okay. So, let A1, A2, Ak are the k different types of objects. And A1 is with repetition, finite repetition with n1 repetition. That means n1 number of A1. Similarly, A2 is with n2 repetition and AK is with NK repetition. Then say I have to take the I have k different types. Now let first we choose the A1 objects. Since I have A1, A2, AK, these are the objects we have, AK, the k different, since I have A1 into AK, k different objects. Then an A1 appears, or A1 is with N1 repetition. So, we can choose A1 objects by NC1 with NCN1, because A1 is with repetition N1. Okay. Now, once I have chosen NC N1 ways of A1, then we can choose A2 from remaining objects. That means remaining objects are A2 objects. Remaining objects are n minus n1, and my A2 is with repetition n2. So, these many ways I can take. So, the same thing if it is for A3 objects, then now my objects remaining n minus n1 minus n2. See, A3 is with n3 repetition, A3 with n3 repetition. So, I have n3. In this way, if I continue, then I can tell my AK, if I choose AK objects, AK type of objects, that with NK repetition. So, n minus n1 minus n2 minus n k minus 1 C n k. So, now we can use multiplication rule. And we can get the number of multiplication this is number of permutations, equal to for the A1 objects NC N1, then it is n minus n1 C n2, then n minus n1 minus n2 C n3, and in this way I will get the for ak n minus n1 minus n2 minus nk minus 1 C nk. So, if we put the values, the n factorial by n1 factorial into n minus n1 factorial, then again n minus n1 factorial divided by n2 factorial, n minus n1 minus n2 factorial, then n minus n1 minus n2 factorial, then n3 factorial, n minus n1 minus n2 minus n3, and in this way if I go, then the last term will be n1 minus n2 minus nk minus 1 factorial divided by nk factorial and n minus n1 minus n2 minus nk minus 1 minus nk factorial. So, the numerator and the previous denominator, they will cancel because it has the same term n minus n1 here, n minus n1 minus n2, n minus n1 minus n2. So, they will cancel and I will be getting the n factorial divided by n1 factorial, n2 factorial, n3 factorial, then nk factorial, and the last denominator will be there. Now, what is this last denominator? See, the last denominator is, if I write here, the last denominator is n minus n1 minus n2 minus nk minus 1 minus nk. So, if we remember the size of S, that is n, is n minus, this size of n is n1 plus n2 plus nk, which is nothing but equal to, this is equal to n only, the size of S. So, this is n minus n is equal to 0. So, I get for the last one is 0 factorial. So, which gives us that our n factorial divided by n1 factorial, n2 factorial, n3 factorial, then up to nk factorial. So, this is my the proof. So, quickly if we see one example. So, we want to compute the number of permutation of the letters in the word, say word is Indian. So, here if I consider the set S, then I repeats 2 times, N repeats 2 times, then D repeats only 1 time, A repeats 3, 6, 1 time. So, this is my multiset, and I have total number is, the size of S is 6. So, my n equal to 6, and I can write the number of permutations. So, the number of permutation is 6 factorial divided by, there are 4 types, I is of, this is my n1 2 factorial, n2 2 factorial, n3 1 factorial and n4 1 factorial. That means, I with 2 repetition, n with 2 repetition, d with 1 repetition, a with 1 repetition. So, I can write 6 into 5 into 4, 3 into 2 factorial, and this will be 2 into 2 factorial, and this becomes 6 into 5 into 2 into 3 is 180. So, in this way that we can apply this theorem of to count the number of permutations for multiset where the elements appear with finite repetition or with infinite repetition, and we can apply to solve the counting problems with permutation.